Okay, so integrated rate laws, there's just a couple of rules that you have to memorize. So for integrated rate laws, there are three main ones that we're going to discuss in the AP Chemistry curriculum. You can see my screen, right?
Yeah.
Okay, so we have zero order reactions, first order reactions, and second order reactions. Each reaction, it follows a pattern of y equals mx plus b, right?
Yeah.
Now your x's are always going to be your time, right? So what is changing? Your time is changing, right? And that's going to affect your concentration. So for a zero order reaction, right, it's pretty simple. You're going to say that your reaction at the end is just equal to the coefficient k times time plus your concentration of your reactant at the beginning, right? And note that this is a negative k. This will be important. Now, there's nothing much to do other than memorize these because we don't know how to integrate in calculus yet. So what we're going to do, we're going to take for a first order reactant, it would just be the natural log of your final concentration equals kT plus the natural log of your initial reactant. And note this one is also negative.
This looks like physics, honestly.
Yeah. Well, would like the change next equals
Initial
VG.
final.
Yeah. And finally,
AT. Yeah.
for a second order, it's 1 over your uh, final minus equals KT plus 1 over your initial. So be concentration of A 0, right? Note that
Yeah.
this one is positive.
Mm-hmm.
So what's happening here? These integrated rate laws basically tell you that if you're given an initial concentration and a final concentration, as well as the time that it took to get from one concentration to the next, it will give you, if it's depending on whether it's a straight line or not, it will give you which order it is, which order the reactant is. So on a graph, if you're plotting just the concentration versus time, right, and you get a negative, then you know that it's a zeroth order, right?
Mm-hmm.
If you're plotting the natural log of your concentration versus time, and you get you get a negative slope, you know that that's first order. Now, if you're plotting 1 over your final concentration, what should it look like if it was second order?
Positive slope.
Positive slope, right? And that should that should make sense. Here
Because you're
it's
positive K instead of
yeah,
negative.
negative slope. No, negative k, so negative slope. Negative k, negative slope. Positive k, positive slope.
Because
Right?
it's just Y equals MX plus B.
A very small little discrepancy here. Whenever you're graphing, it's not going to be graphed as the final concentration over time. It'll just be concentration over time, or natural log of concentration over time, or 1 over concentration versus time, because like final doesn't make sense, but the rest of the concepts are all still the same. Just know that you can solve for multiple parts. So let's say I know that my reactant is first order. I know its initial concentration as well as its final concentration, and I know its rate. I know that's and I know the rate constant k. Then I can just reorder my equation and solve for t, right? So it's all dependent.
What does the constant K represent, though? Is it just literally just the constant of proportionality, or?
Yeah, so it'll be, in this case, k would be the slope for all these different lines. So k is just a reaction constant that will differ from different reactions. Now let's work with some applications of the integrated rate law. Here we have three different graphs of the concentration of NO2 versus time, the natural log of the concentration of NO2 versus time, and the inverse of the concentration of NO2 versus time. Now you can see here that the first two are curves while the third one is a linear positive line. Note that this curve should actually be lower, but the main point is that it's a curve and not a linear negative line. So if it was a linear negative line here, it would be zeroth order. But since it's not, this is not zeroth order. Since this one is also not a linear negative line, it's not first. And we know that for second order, it has to be a linear positive line. And since whenever you graph 1 over the concentration versus time, you get a linear positive, you know that it is second order. Now, I have two of my points. At 5 seconds, it's my concentration of NO2 is 0.0165 molar, and at 15 seconds, 0.00620 molar. Now, what I'm going to do is I'm going to set up an equation. Let's say it asked me, what is the rate constant K? Now, note, the rate constant K is just the slope, rise over run. So what I'm going to do is I'm going to write out my integrated rate law for a second order reactant, which states that 1 over NO2 at some final time t equals positive K times t, or I can write this as delta t, but I'm going to keep it as t for now, plus 1 over my concentration of NO2 at some initial point. If I were to plug this in, I'm going to plug this in, it's 1 over my final. In this case, I'm gonna consider my time after as the final. I'm gonna mark this one in magenta, this one in red. So it'll be 1 over 0.00620 molar. This is gonna be equal to my K. Now my T, make sure you don't put 15 seconds here, because 15 seconds is the time that it is 0.00620 molar. That's not the time it takes for it to get from our red to our magenta. So it'll be 15 seconds minus 5 seconds, which is just 10 seconds. So make sure you understand that difference. And then we're going to add it, put this in red, by 1 over 0.0165 molar. Now if I do the math, I subtract both sides by 1 over 0.0165 molar, and if I divide by 10 seconds, I can get a value of K. So plugging it into my calculator, I can get that whenever I subtract it and then I divide it, or just change in y over change in x to get my positive K slope, I'm going to get a number of about 10.07. And that all makes sense because K's are usually between 0 to 10 or 1 or 1 to 10-ish, as long as it makes sense. So in this case it would be 10.07. As for my units, recall that whenever I subtract these two values, I'm getting something in inverse molar, and then I'm dividing by seconds. So that's the same as timesing by inverse seconds. So it'll be inverse molar, inverse seconds. Another way you can think about it is that since this is a second order a reaction, the K has to be in terms of the units that a second order reaction would have, which is just inverse molar, inverse seconds. Make sure that's clear. Now, to clearly show that our K is the value of the slope, what we can do is if we graph it in the form of y equals mx plus b, you can see this is y equals mx plus b, right? In this case, my b is your y-intercept. So whatever your y value is, whenever your x is 0. So in this case, that'll be 0.100, the inverse of that. And if I graph this line, look, it goes through all my points, so therefore my slope is my K. Now building off of that, a follow-up question could be, what is the concentration after 20? A follow-up question could be, what is the concentration after 25 seconds? So what I can do is knowing my value of K. So now if I have to find what the concentration is at 25 seconds, what I can do is I can basically just say that my concentration of my NO2 at some time, let that be 25 seconds, equals my K, 10.07 inverse moles, inverse seconds, times my my elapsed time, which would be 25 seconds, minus, now what is my initial concentration and my initial time? Well, that can be whatever you want as long as you were consistent. In this case, I'm going to use these values in red. So 5 seconds plus, in this case, it'll be 1 over my concentration of 5 seconds, 0.0165 molar, because it's 1 over here, so it has to be 1 over here. Recall, this is our second order reactant equation. Solving this out, I get 1 over NO2 T around 262 inverse molar. How do I know the units? Well, these two S's will cancel out with this S here, and it'll be inverse molar plus inverse molar, right? 1 over molar is inverse molar. So how do I convert this? Well, if I just flip my equation on the left side, I get NO2T. That means I also have to flip it on the right side. So I'll take 1 over this value. So whenever I do 1 over my value, which is around 262, I get 0.00382. 0.00382. And I know that my units are going to be in molar because 1 over inverse molar is molar. So that's my concentration at 25 seconds of my NO2. And to check, what I can do is I can plug this into my calculator. I can do at time 25 seconds, it has to be 0.00382. And recall that we are graphing the inverse concentration versus time. So if I raise this to the -1, it's the same as inverse, and see it falls directly on that line. So those are the steps to get from your graph to your individual points, to finding the reactant order, to finding your slope or your rate constant K, and then finding your concentration at an unknown time.